Okay, last time we had what? What do you remember? Last time we had fixed theorem. Frenet-Serret theorem. Right? So we have alpha unit speed, and we assume curvature is not zero. Then what is the T prime? We have a Frenet-Serret apparatus, curvature, torsion T and B. So everyone knows what they are, okay? And T prime is capital N, and N prime is minus curvature T plus torsion B, and B prime is minus torsion N. Then, right? If you remember the matrix form, then it'll be easier. Remember. Then we had a definition, and we did two examples. The general helix. Sometimes we skip saying the general. The alpha is a curve is a helix. If the alpha, then what? Alpha is a helix if the inner product of T and U, that is constant for a fixed unit vector U. Okay? Then if that is true, then we say alpha is a helix, a general helix. And we had a note for that. If you remember the product, and this is what? I use this either way, the product, right? So that is the length of the T times the length of the U and cosine theta, right? So these are units, so this is a cosine theta. So that constant means what? This constant means theta is a constant, right? So this constant means then theta is constant, the angle. So that means angle between unit tangent vector and that fixed constant vector, the angle between these two is constant. Okay, so we call this is a PG, and that U is the axis of this helix. Okay, so we had two examples. Actual helix, circular helix, that is a helix, right? It should be. And any plane curve is a helix in this sense. Okay, because any tangent vector to the plane curve is what do you take? What can you take U for that plane curve? Right, the B, right? Binomial vector. We take the B binomial vector for U is a unit, right? Plane curve. What can you say about that binomial vector? That is look at the corollary of this one. We have three equivalent conditions. Curve is a plane curve, and torsion is 0, and B is a constant, right? So B is constant and unit. So if you take the U for that B for the plane curve, then tangent to the plane curve is orthogonal to the B. So the angle between T and U is 90 degree, right? So tangent to the plane, and if we take the B, the U as the B, then is the angle between these two is 90 degree, which is constant. So plane curve is a helix in this sense. Okay. Then next one actually here is another corollary to that. 1802. French mathematician Lancret proposed this. Lancret proposed this problem in 1802, and actually he could not solve it. Another person found the solution, but this somehow this name is named after him for some reason. Okay, so this one, a unit speed curve alpha with non-zero curvature is a helix. That helix, if and only if there exists a constancy such that the torsion is constant, that constancy times the curvature, which means the ratio of this, ratio to the torsion to the curvature is constant. If you have that special ratio, then the curve is a helix. So this is very interesting fact. Okay. So then let's see how it works. Okay, let's see the proof. So suppose that the alpha is a helix. Then we have a condition. The inner product of t and u. So that is cosine theta. Because we assume alpha is a helix, so we know that there is a fixed constant vector, unit vector u, such that the dot product, inner product of t and u is cosine theta. Okay? Okay? Okay. Then here, theta. What happens is theta, that angle, pitch, is integer multiple. Let's see what happens. Like a pi, 2 pi, 1 negative pi, 1 negative pi, any integer multiple. Then what happens? Theta is the angle between t and u, right? So if theta is a pi, that means what? T and u. Angle between t and u is a pi. That means u is a minus t. If it is 2 pi, then yeah, u is the same as t. Right? Okay? Because we know that theta is the angle between these two. So if the angle is the pi, then u is minus t. If theta is 2 pi, then it's same. Okay. Then what is u prime then? Either case. U prime is minus t prime, right? Or u prime is t prime. But what is u? According to the definition of a helix, u is fixed, which means constant, right? So that is t prime is 0. Either case, either that or that. We got t prime equals 0. If t prime equals 0, then what is the curvature? 0, right? So it's a contradiction. Actually, we assume that we have non-zero curvature. So it's not going to be a case we consider. So theta is not an integer multiple. So we need that factor.
So by integer multiple, you always mean integer multiple of pi. By saying that it's an integer multiple, it's always an integer multiple of pi.
Okay. Okay. Then let's see. So let's see. Let's come back this. We know this is constant. So this should be 0. Right? By the definition of helix. So we know that that derivative of the product, we have right? Product rule plus t u prime. And we know that this is 0 because it is a constant vector, so this term is 0. And I just erased that. This one, t prime is a curvature n, right? So we can take out curvature and then okay. Then we assume curvature is not 0 anywhere. So this is not 0. So we have that dot product and then u is a 0. Right? Okay. So what do we know? You can write u this way. From A, T plus B, N, and C, B. Because T and B are orthonormal bases.
How do we know that at the very beginning the derivative is equal to 0?
Helix. That is constant. So derivative is 0. Right?
Okay.
Yeah. So, okay. Then we can write u, this fixed existent vector, is in terms of t and b orthonormal basis. Okay. So we just found that this u and n, the product of n and u is 0. So this tells b is 0. Right? We figure out b value, the dot product of u and n. Okay, that is 0. Then let's figure out this a and c. Okay. So what is a? We can get a, same, dot product of u and t. What is dot product of u and t? Yeah, it's there. It's a cosine theta. Right? So a, that coefficient to a is cosine theta, constant. Okay. Then we have to figure out c. Okay. So what is length of u? Length of u is 1, right? Unit vector. So u, that is 1. So you have 1, right? Cosine theta t plus cb, cosine theta t plus cb. Then what do you have here? We have a tt, cosine square theta, t dot t is 1, t dot b is 0, b dot t is 0, that plus c square. So what is a good thing? I mean, what can you use for c? Sine theta. So c, here sine theta. So we determine that axis this way. So here It says that u is our axis of the helix is cosine theta t plus sine theta b. Okay, that is good because if you know the curve is a helix and this we know that angle, then we can determine the axis, right? Because u is given as cosine of the angle times t plus sine of that angle p times b. Okay. Okay, then let's see. Let's see this one then. What is u? This u then. This u is a fixed constant vector. So if you take the derivative, what do you have? That is a 0, right? Because u is constant vector. So let's take the derivative. These are constant. So we have this. Let's see what we have here. Cosine theta t prime is then plus sine theta negative tau, right? You worked in Minkowski spaces. Yeah, change the sign. Okay, so then let's see. You can simplify this k kappa cosine theta minus torsion tau sine theta. Let's take out all the the function part, okay, and vector n, and that is equal 0. Okay. So what is equal 0 then? This n is a vector, not 0. So this has to be 0. So that means the curvature cosine theta equals torsion sine theta. Okay? Then what? Then we have a theta. The angle is not the integral multiple, not pi, 2 pi, negative 2 pi. It's not that one. Okay? So we divide sine theta because sine theta is not 0 for those angles. So what? Tau is right. Tau is cosine theta over sine theta and curvature. Right? We know these are constant, so we can take that one as a c constant. So there is a c. There is a constant c such that torsion is a constant multiple of the curvature. Okay? There we see. It is very beautiful, right? It is good. Yeah. It works very nicely. Yeah. Okay. The other way is kind of we go backwards. We go backwards. So here we assume there is a constant c such that the torsion is a constant multiple of curvature. So we assume we have such a constant c. So simply take c, that constant c, as that cosine theta over sine theta, which means a cotangent theta. Let's take constant c that way. Okay. Then oops. Then take and choose u the same way. choose u to cosine this theta t plus sine theta b. Then this is constant, so this is constant. Okay. Then what? Is u length is 1. Is 1, right? Then what is the t and u? That is cosine theta. Okay, that is a constant. So this shows alpha is the helix. So we go actually the backwards. We choose the constant c to make that happen. In fact, so this proof shows. Actually, this work shows how that we have the helix then using these relations, using this ratio. Okay. So actually, here's a note. 1845, 43 years later, another person, the Saint Frenet, this person proved this theorem. So he proposed it in 1802, but that person finally proved this whole thing after 43 years later. It looks simple, but it wasn't simple at the time. Okay. And actually here, if ratio of this one is constant, right? Then what is the question that we can think? If the ratio of this one is constant, we know that the curve is a helix, right? So what happens if ratio is what is the next simple case next to the constant? Next simple function we can think. Constant and we have many kinds of functions. But linear function, right? So the ratio of torsion and curvature is a linear function. If the ratio satisfies this, okay, then it is known that alpha is a rectifying curve. It's very interesting. Actually, the thing is that until 2003, my thesis advisor found that special curve satisfying the ratio of this is a linear function. But before him, there's no result about the curve, space curve satisfying this. This is a simple ratio then. So he had many different kind of categorization of the rectifying curve. This is one of those. Okay, and then Yerim and I actually 5 years ago, what happens if A equals 1 and B equals 0? Simply like that. Then what is the curve? Then that work was done with the Yerim a few years ago. Okay? So this is a very special to me, actually, this theorem, this factor, because after Yerim and I worked this theorem, this corollary, then we had a question, what is next case? What happens if it is linear then? And then I found the paper there. Yeah. Okay? Then later then I'm going to show you how we can get that problem done then. Okay. Okay, then I'm going to show you the 4 more propositions. Okay. Alpha is a straight line. If and only every tangent line goes through a point. So this way of a proof is very straightforward. Okay. If a curve, is a straight line, then tangent line to the straight line is same itself, right? So that every tangent line goes through any point on the line, right? So this is obvious. Okay, this way. And the other way, I'm going to give you that one as a homo.
What's x?
X naught on the line. Let's put this way more correctly then. X naught is a point on the line, yeah? So the other way, I'll put that in the homo. Okay, it's similar to the one that you have, the number 3. Yeah, probably you can see, you can get some idea after I do the home proposition next one, 4.8. Okay? 4.8 is the one. Is a unit speed, regular curve, such that every normal plane to alpha goes through a given point x naught. Then we can say something about the curve. Then alpha lies on a sphere. So let's see why. So if you see the curve, then we compare the 2 points. So here's tangent and normal and binormal. Tangent, normal and binormal. And this is N, this is B, okay? Okay, then the assumption is that the alpha is a special curve satisfying this condition. Then every normal plane to alpha goes through a given point x naught. Here, the normal plane at this point is a plane spanned by N and B. Okay, so this normal plane at this point goes through x0. And also, the normal plane at different point on the curve. So that is a normal plane, right? That normal plane goes through this point as well. So let's make plane bigger like that. So we have this normal plane and next bigger normal plane. So it's like that, okay? So every normal plane meet actually goes through x0. That's the assumption of the curve. All right? Okay? Normal plane at each point on the curve has x0. Okay? They share the same point x0. That means what? That's a vector from x0 to the curve, to the point on the curve. That is this vector and that vector. So that lies, these vectors are in normal plane, right? That means this start with, this is in normal plane, this start with t is 0. Okay? Okay. So because of the assumption, we can say that one. Is that right?
Does it have to be sphere?
What? This one?
Yeah.
Yeah, I'm going to show the why. So with that condition, let's figure out this one. Let's see. We found this one. Okay. Okay. We know this is true. Let's take the derivative of that. We don't know what that is yet, but let's take the derivative of this portion. So how can we take the derivative of this? Product, yeah. Okay, so product first. What is the derivative of this? Alpha prime is a unit speed. So derivative of this is Lancret. Derivative of this vector t, and leave this the same. So we have x0, okay, and plus leave first the same, and take the derivative of second, that is t. Right? So we have 2 of this. Then what is that? We have this is a 0 by our assumption. Okay? So that means what? That means this shows actually this magnitude, right? The square of that magnitude is this much. That is constant. Is that okay? Okay. So constant, we can put this one as A. So this is constant, but this is the magnitude of length of this vector. So it's bigger than or equal to 0. It's positive constant or equal to 0. But let's see what happens if the magnitude is 0. If the magnitude is 0, then what is the case? Then this has to be equal to 0, right? Then alpha s is x0, is a point, and that is not a regular curve. So let's see, unit speed regular. Okay. is not the case we should consider. So what do you know then? It's not 0, so that has to be positive, strictly positive constant. Okay? Okay, that means what? That means what? That means length of this vector, the length of this vector is constant, right? So what can you say about the curve then? Every point on the curve, same distance from x0, right? So what do you know then? That means alpha lies on a sphere centered at x0.
How about if it lies with a cone? How about if it lies with a cone?
The cone?
Cone, yeah.
The distance changes. Right, from the origin, let's say x0 is 0, then points on the cone, the distance from the points on the cone and 0 is changing. It's not, doesn't stay constant.
Right, but if you take this like the horizontal plane.
Yeah, but if you look at that one, then it's a circle, but yeah.
That's the circle.
I mean, we consider this one in RC, right? Okay. If it is in the R2, then it's a circle, right? Okay. Okay. And that's it then. So if you change that to osculating, then a similar way then. Okay, it's almost 3. Okay. Then next one. Same unit speed, non-zero curvature, alpha lies on a plane. We have a plane curve. Another if and only if your condition. Plane curve, then torsion is 0 and B is constant. We have that 3. Another one is every osculating planes, what can you say? Alpha lies on the plane. Then osculating planes are parallel. Okay? It's quite clear then actually here. If you go this way, alpha lies on the plane, then what is the osculating plane? The same, right? The plane that has alpha in it. So osculating plane is that plane, same plane. Okay. If you go the other way, if you assume every osculating planes are parallel each other, that osculating is the planes are what? Planes orthogonal to B, right? So if every oscillating planes are parallel each other, that means B same, right? B is the same. B is constant, right? So one of the 3 conditions for being a plane curve is B is constant, right? So that is plane curve. Okay. The next one is about the spherical curve. Okay. Okay. So alpha is a unit speed. alpha is a unit speed curve lying on a sphere. We call that is a spherical curve. Then curvature of the curve is not zero. And if a torsion is not zero again, then we have that equation. Alpha is minus m, that m is the center. Okay, can be written as minus rho n minus rho prime sigma. And here rho is a 1 over curvature, and sigma is can you guess what? We have a curvature and we have a torsion, right? So 1 over torsion. So we call this rho is a radius of curvature because it is a 1 over the k, and that is a radius of a torsion. And it's called the radius of a torsion. Okay, so let's see why. So similar thing we have here, okay? So we have alpha s minus m, that is 1. The distance from the center to the point on the sphere, that is r, right? Radius, so it's r squared. So according to the assumption, then we can write that equation. Then let's take the derivative and see. We use a lot of derivative, right? So take the derivative to this expression. Then it will be t alpha s minus m is 0, right? We just see it right there. Product rule. Product rule, we have 2 of those, and r squared is a constant, so that is 0. Right? Let's take the one more derivative. One more derivative. Then we have a t prime, and this is t plus 1. T and t, that is 0. Can I erase that? Okay. So that means, again, Frenet-Serret theorem, this is a curvature n. So this is curvature n, t, over there. Right? The plus 1 equals 0. That is something wrong. That's n t prime. Did I do wrong? Oh, no, I did wrong here. Take the derivative of this. What should be there? Derivative of that?
Yes.
Yeah, alpha is minus m. So t prime is, this is right. We have alpha s minus m plus 1 equals 0. So for that. So we can take out k, kappa, okay, and alpha s minus m. plus 1 equals 0. Right? Right? So, is it possible to have a kappa curvature 0? No. If kappa is 0, we have a 1 equals 0. So this expression says kappa is not 0. Okay? Okay, then that's this one. Okay. Okay. Then I think I need more time to finish, more than 4 minutes. It's okay to continue a little bit further? Or, yeah, I'll continue next time then. Okay, I'll finish the rest next time then. I'll stop right now. Then. Okay, yeah.